Hi, folks. So this is my Jim Bob problem, which I dearly love because I get to say Jim Bob. It's also all about family and physics too. So before I get started, I'll say that this one is actually fairly complicated. It's actually also useful to help you to understand um, how to do one of the last homework problems in homework number 3. So that being said, we'll go ahead and get going. It says Jim spots his long lost cousin Bob at a family reunion. Excited, they run towards each other to hug. They are initially separated by a distance of 20 meters. Jim's acceleration is 1.1 meters per second squared, and Bob's is 1.5 meters per second squared. Then we're asked the question, how far has Bob traveled when they meet? All right, so in order to get going on this, the first thing I need to do, just like we always do, is draw a sketch. Okay, so there's Jim. And here's Bob. All right. And we know that they're going to start running towards each other. Looks like Bob is probably, let's see, Jim is 1.1 meters per second squared for his acceleration. Bob's has a size of 1.5. So Bob's going to cover more ground than Jim is. There they are together. And so that's Jim, Bob. There we go. I had to do that, Jim Bob. Let's see. What do we know? We know that their initial separation is a distance of 20 meters. All right. And then we want to start thinking about some physics things. So first off, Jim's displacement goes there. So that's delta x for Jim. That's supposed to be a delta x for Jim. And then Bob starts over here and his displacement goes this way. Boop, boop, boop. So these two arrowheads should meet up though. So something like that. So this is delta x for Bob. All right, so there's my displacements. With the other things that we know is that they both start out from rest. And we're given the values of their acceleration. We're given the sizes of their acceleration. So just keep all that in mind. Now, let's see. And the other thing is this 20 meters there. Our next step on any problem is to define the positive direction. So I'm going to, just like we usually do, define the positive direction to be to the right. Now, this has a little bit of a consequence because one thing we notice is that Jim's displacement is to the right. Jim's displacement is positive. On the other hand, Bob's displacement is to the left. So this delta x sub b actually has a negative value. All right. So what we would think is, well, let's see, the distance that Jim travels plus the distance that Bob travels has to total to 20 meters so they can meet. And that's absolutely right, that the distance those two guys travel totals to 20 meters. On the other hand, if we talk about displacement and realize that Bob's displacement is negative, that delta x sub b is going to be negative, that effectively means that, well, let's see, Jim's displacement minus Bob's displacement is going to total to 20 meters. Because say Jim's displacement is 8 meters, that'd just be positive 8. And Bob's displacement, his displacement is to the left, his displacement would be negative 12 meters, I guess. Well, in this case, 8, we would have to stick a negative sign in front of that, in front of Bob's displacement, because we would want to have our two numbers add up to 20. So 8 minus a negative 12 is equal to 20. That's why there's a minus sign in there. Sorry, I just got an email and it was a little distracting. I should have shut down the chime. All right, so that's important. We're going to use that. It looks like I've run out of space, so I'm going to move to another slide so that I can start writing some stuff down. All right, so let's make tables for Jim and for Bob. So delta x sub j, we don't know that. We know that Jim's initial velocity is 0. We don't know Jim's final velocity. We know Jim's acceleration is 1.1 meters per second squared, and we don't know Jim's time. Okay, well, what about Bob? So for Bob, let's see, delta x sub b, we don't know what that is. We know Bob's initial velocity. He started out from rest. We don't know Bob's final velocity. What about Bob's acceleration? We know it's has a size of 1.5 meters per second squared, but remember, it's to the left, so we need to put in a negative sign there, negative, okay. And then delta TB, we don't know that either. So I look at each one of these two tables of variables, and notice that I got a real issue because I only know 2 out of the 5 things in each one of those tables. And I told you guys we need 3 out of the 5 in order to get anywhere. So we can think, though, about the connection, some possible connections between Jim and Bob. They both start out running at the same instant. And of course, they stop when they meet each other. So in this case, and it won't be the case for your homework problem, but in this case, the time that they travel is the exact same. So what I'm going to do is I'm just going to fill in our table here that this is delta t for both these guys. All right. Now let's see. I would like to know the displacement. I know that I've got that relationship that I wrote on the last slide, that delta xj minus delta xb is equal to 20 meters. And then I can start thinking through my kinematic equations and think about which one might be the most helpful. Well, let's see. There's one that goes delta x is equal to v naught delta t plus 1/2 at delta t squared. And in that one, let's see. What do I have? I've got time, initial velocity, acceleration, and displacement. So in looking at my list, let's see. Displacement is what I want to get to. Okay, so I would really like to know what the displacement is. I know initial velocity, I know acceleration, and I don't exactly know what time is, but I know a little bit about it. I mean, I know the time is the same for the two guys. So I'm gonna choose that equation as maybe one that I could start poking at. So let me write that equation out for both these guys. So delta x j is equal to v naught j times delta t plus 1/2 a j delta t squared. Let's do the same thing for Bob. Delta xb is equal to v naught b delta t plus 1/2 times Bob's acceleration times the time squared. All right, so check this out though. We know that their initial velocities are 0, so this entire term is going to go away. Likewise, that entire term is going to go away, because when we stick in 0 for v, well, then we would have 0 times delta t, and 0 times anything is just 0, so that entire term goes away. So now we're left with something slightly easier. We've got that expression right there that represents Jim's displacement, and that expression right there that represents Bob's displacement. Let's take both of these and stick them into that equation right there. That equation right there shows how their displacements add together to get to 20. So let's do that. Let's stick these guys into that equation. So we end up with 1/2 Jim's acceleration times delta t squared minus 1/2 Bob's acceleration times delta t squared is equal to 20 meters. Let's go ahead and stick in those values for acceleration. And then let's carry out the math a little bit. So this gives me 0.55 meters per second squared times delta t squared. And then I've got minus 1/2 times a negative 1.5. The negative signs are going to cancel there. I'm going to get plus 0.75 meters per second squared times delta t squared is equal to 20 meters. All right, so if I add 0.55 and 0.75 together, I've just got a couple coefficients there. Like say I've got, I don't know, something like 3a plus 5a, that'd be 8a. Well, 0.55 t squared plus 0.75 t squared would be what? Let's see here, 1.3 t squared. Okay, so let's take this on to the next page. So 1.3, I'm adding those two coefficients together. Easy for me to say. Divide both sides by 1.3. I get delta t squared is equal to 15.4 meter or 15.4 seconds squared. Take the square root of both sides. If I take the square root of both sides, I get that my delta t is equal to 3.92 seconds. You know what? That is really useful because now what I can do is I can turn around and stick that into my displacement equation for Bob, which said 1/2 times Bob's acceleration times delta t squared. That's an equation from the previous slide. And then stick in that value, negative 1/2 times negative 1.5. Well, where'd the negative 1/2 come from? Oh, that's me. I just added that in. That's not so good. That negative sign should not be on the front of there. Whoops. Sorry. No extra charge for mistakes. So at least I caught it. Okay, negative 1.5 meters per second squared is what that's supposed to say. There we go. Times 3.92 seconds squared. And I get the result that Bob's displacement is negative 11.5 meters. So that's Bob's displacement. So now the question is, are we done? And we think back to the original question, and the original question said, how far does Bob run? So that's really asking for a distance. It's not asking for Bob's displacement, but rather the distance he traveled. So I probably just want to report the size of that displacement. And the size, the magnitude is always positive. So the 11.5 meters is the distance that Bob travels. All right. So tricky things in this one are making sure that we understand the link between the distance between Bob's displacement and Jim's displacement, and also the whole fact that Bob's displacement is negative because he's moving to the left, and we define the positive direction to be to the right. All right, you guys will do something kind of similar to this. There's one extra step involved. For the problem I have in mind, it's not two guys running towards each other. It's basically one ball is dropped down and one ball is shot up at slightly different times. And then something about where do they meet. But you can use some of the same ideas that I've shown here to help to inform your thinking on that one. All right. So I think I am done with this. Now all I have to do is figure out where the stop button went.